So, welcome everybody. As I said, yeah, we have some initial technical problem here. I'm not sharing anymore, right? So, try again. Okay, now should be good again. Good. Okay, so again, welcome everybody to Approx 2021, again online, unfortunately, despite the initial hopes. But okay, we'll try to do the best. So, okay, I will just do a couple of minutes of introductions about this conference and how it's gonna be held this year. So the PC has done great work in selecting 27 papers to make a great program for this year of Approx. You will see 26 talks though, because there have been a soft merge between two papers, and actually this would be exactly the first talk of the session. So the 26 talks are actually scheduled in 6 sessions for Approx. So the sessions are quite short, of course, because of time constraints, time shift all over the world. So the short talks are actually 8 minutes plus 2 minutes to do the changing between speakers and also to ask some questions, but very short ones. I have to say that if you want to ask questions, then you have 2 possibilities. The first one, in order to be heard by the whole crowd, is to actually change your position. So you have to go to a mic spot when there's a mic spot, and then you will be able to speak. Or, which I think is more practical, at least during the talks, you can actually write your questions on the common chat. And in that case, I will be reading it to the speaker. So since this is actually might not be the best possible way actually to ask questions, so after each sessions, there is a discussion phase of 20 minutes. And during this discussion phase, all the speakers of the previous sessions will be available, and actually they will also have a small poster that could also be one slide just to actually summarize a bit at the topic of the previous talk. And the goal of this is that you can then go and with your avatar in Gather Town, it becomes way easier maybe to ask questions and discuss, and also the authors, of course, can discuss their paper among themselves. So these, as I said, are short talks of 8 minutes, but long pre-recorded talks and proceedings are already available, and both the pre-recorded talks and the proceedings are actually 27, because the 2 papers that have been merged for the soft talks, they have their own pre-recorded long and proceedings. You can find them. There is a link on the website of Approx, but also pre-recorded talks should be available also here in Gather Town on the TVs. Okay, some important things that I would like to mention. So first of all are the plenary talks. So the plenary talks are actually joint with random, meaning that, as you know, random and Approx are held in parallel, so there are parallel talks. But that's not the case for plenary. So the plenary are actually just 1 talks. So today, Monday, there will be the plenary talk of Yelani Nelson from UC Berkeley, which will talk about the survey of random projections. And on Wednesday from 6 to 7, there will be a talk of Vera Traub from ETH Zurich. And she will talk about better than 2 approximation for weighted 3 augmentations. And this is a very recent results and very exciting for the approximation community. So I'm looking forward to both the talks, and I think that would be great plenary. So as you see here, there is an activity for Monday from 6 to 7 and Wednesday for 6 to 7. And I'm also always referring to Central European time. So what about Tuesday? Well, Tuesday, there is actually the social event which is going on. And okay, of course, the goal, as in every social event of a conference, is to socialize, so to meet people and new people to discuss and all things. But in addition, hopefully there will be some funny activities, and in particular, Mary Wooters and Clement Cannone have organized a few activities that to share. So the first one is that there will be a TCS themed game of trivia on the virtual chair venue. And for this, you are, of course, welcome and encouraged to participate, to play, but you can also suggest some good trivia questions in the spirit. If this is the case, again, you're still on time to submit some questions that could be used during this game. You can go to our webpage, and there, if you go to program and you see a link to the social activity, and you will see how to suggest questions if you want to. And second, there will be Approx random cartoon caption contest this year. So how this works again? So here there are two cartoons that are in need of some funny captions, and you can submit your own possible answers, and with the possible TCS flavored. And during the social event, it will be announced the winners of this contest. So, okay, I hope that, you will enjoy the conference, and that it would be a successful 3 days of activity. And that's all I want to say before we can now start the first session, which I actually chairing. Okay, I hope everything was clear. Good. So our first speaker today is Valdo Galvez. Actually, this is the talk that I mentioned before that is actually merged. So there are two papers merged together. So Valdo Galvez will share with Malte Tutas. And okay, I'll let Valdo start.
So thank you very much for the presentation. I'm Waldo Galvez, and I'll present our work, Approximation Algorithms for Demand Strip Packing, which is joined with Fabrizio Grandoni, Afruz Gevalamelli, and Cambia Codamoradi. So let me first define the problem. So we are given a timeline of fixed width and, let's say, arbitrary height, and a set of tasks which are represented by rectangles characterized by their width and their height. And our goal is to find a schedule of the tasks into the timeline so as to minimize the peak. And here by schedule, we mean that for each task, we assign a subinterval of the timeline matching the width. And then for each point in time, we consider the whole accumulated load on that point, and the maximum among them will be the peak. So this problem we call demand strip packing, and it's also called as peak demand minimization, because of its resemblance of the classical geometric strip packing, where the instance is the same, but the requirement is that the tasks are embedded as rectangles in the plane. So from here you can see that this schedule can be turned into a geometric schedule of the same peak, but as noticed in the literature, there exist instances where this is actually not possible, even for the case of squares. So what is known for these two problems? Both are hard to approximate within a factor better than 3/2. And for geometric strip packing, there is a long sequence of improving results, reaching the current best approximation of 5/3 plus epsilon due to Harren et al. While for DSP, despite of the efforts, the best known is the two approximation due to Steinberg, which is actually an algorithm for geometric strip packing, and nothing better is known. So our results, we want to show that there exists a 5/3 plus epsilon approximation for demand strip packing, plus two side results, like a tight approximation for square tasks and a p-task for short tasks, although I will focus on the first result. And here I want to stress out that the results for geometric strip packing improving on 2 do not carry to the demand setting because they heavily rely on the geometric constraints. So just to give a quick glimpse of how our algorithm works, as usual in this setting, we classify the items according to their dimensions. So we say they are tall, large, horizontal, and narrow. And our algorithm consists of 2 main steps. First, we find a solution for all the items which are not narrow, of height at most 5/3 plus epsilon. And then we devise an algorithm to include the narrow task on top of this solution. So for the packing of not narrow tasks, what we want to do more or less is to rearrange this solution into something with a structure that we can guess, which roughly translates on finding a solution where all the tall tasks are together and sorted by height. This we show that can be done at the expense of extra 2/3 heights, which is the accumulated load of the task we had to remove in order to rearrange. By doing so, we get a solution with some induced profile of height at most 5/3 plus 2 epsilon, where we want to include now narrow tasks. So our second step, where we make use of the demand feature of the problem, now here we want to, in a sense, push all the tasks to the left so as to get more structure. And what I mean by this is that if I can shift a task by 1 unit to the left in the timeline, I do it. So and I exhaust these steps without surpassing threshold. So we get a solution with a much better structure in the sense that it accumulates load among the first points in the timeline, while from this point to the right, the profile is decreasing. After arriving to this nice structure, it's possible to include the narrow task via a very simple iterative algorithm without increasing the peak. So what are the open challenges here? Is it possible to get a 3/2 plus epsilon for DSP or for GSP even? What is the exact gap between GSP and DSP? And what can be said for demand versions of other geometric packing problems? I think there are many interesting directions here, and I will be happy to discuss them with you in the poster session. So thanks a lot, and I will leave you now with Max, who will continue with his approach to the problem.
Okay, so thank you, Valdo. I hope you can hear me. Screen. Okay, so 3 minutes from me now to give you a very brief overview. So I'm Max, and this was joint work with my supervisor Klaus Jansen, Avendam Khan, Morlin Rao, and Malte Tutas, who actually also produced the video for you. So our results, of course, the first one is the 5/3 plus epsilon approximation for the problem we call NPDM here, which stands for non-preemptive peak demand minimization. And we utilize the second theorem, which is basically an AEPTAS result, saying that we can asymptotically approximate the problem up to an additive factor of the largest energy demand, here denoted by Emax. So a brief overview about the 5/3 algorithm is, well, to have in the first step some computation of some more advanced lower bounds for the optimum value. And afterwards, we ask whether the instance is Steinberg structurable. And if so, we use Steinberg's algorithm to solve it, at least in some remainder instance. And if not, we can apply our AEPTAS result and have some necessary repacking afterwards to guarantee our 5/3 approximation. So for the Steinberg structurable instances, there are 2 main cases, in some sense complementary to each other, where we know that in the one case, the total processing times of the total processing time of all the jobs with a large energy demand is large, and on the other hand, we know that the total energy demand of all the processing, all the jobs with large processing times is large. Yeah? So, and these are the first steps to have some structuring of these jobs, and in all cases, we can then guarantee to end up with situations like this, where we have some window to guarantee the use of Steinberg's algorithm for the remaining instance. So for the AEP-TAS result, we have some classification of jobs by size, very similar to the result of the group around Valdo. And yeah, so we are able to pack all the jobs into a schedule with a peak energy demand of 1 plus epsilon times the optimum value and some additional. And how to do that? Well, we remove a few of the scheduled jobs of an optimal solution and have some structural argument that we can iterate all the possible structures and polynomial time compliant to the structure by linear programming. And especially this additional container we have at the top then can be large in one direction and thin in the other, or the other way around. Yeah, so we can choose between these two options. Yes, of course, the open problems here also very obviously we have some gap to close. Is there an approximation algorithm between 5/3 and 3/2, or may we have some stronger hardness result here? Thank you.
Okay, thank you very much. As I said, let me remind that if you want to ask questions, you can write them on the chat. I think that's the easiest. Meanwhile, just two things I want to say. So first, I want to apologize, Max, because I announced the wrong speaker, like the speaker of the video instead of you. Okay, that's fine.
No problem.
No problem. And then actually, no, I have a very quick question. So you both groups, you have this 5/3 plus epsilon approximation for the same problem, and I mean achieved completely independent also with the independent techniques. What about the running times? May I ask which one is the best?
So which one is the best? Valdo?
I would say that Max's algorithm is faster, but just because we didn't bound very carefully the running time of our algorithm, but ours is based on enumeration techniques, which are actually quite slow. So my guess would be that our algorithm is slower.
Okay, good. Well,
evaluate that, yeah.
Yeah.
Yeah, I mean, it was just the first thing that can come as a question, to differentiate since the approximation factor is the same. Okay, good. So thank you both.
Thank you.
And yeah, we can move to the next talk. Okay. So next speaker should be Eklavya Sharma.
Hello.
Is it here? Oh, yeah, here you are. Good. Yeah, I still see the screen of Max though. Okay, great.
Just a minute.
No problem.
Is my screen visible now?
Yes, that's great.
Okay, let's start now.
Yes, you can start now. Yes.
Yeah. Good morning, everyone. I'm Eklavya Sharma, and today I'm going to talk about my work on tight approximation algorithms for geometric bin packing with skewed items. This is joint work with Professor Arindam Khan at the Indian Institute of Science, Bangalore. Let's first start with the two-dimensional geometric bin packing problem. In this problem, we're given a lot of rectangular items that are axis parallel, which means that each edge of each item is parallel to either the x-axis or the y-axis. And we're also given an infinite supply of identical rectangular bins. And our task is to pack all of these items into the minimum number of bins. This problem finds applications in a lot of places. For example, especially in the metal cutting and the wood cutting industry. Here, raw material is often available in large standard size sheets, and from those we want to cut out smaller rectangular pieces of desired sizes. This problem also shows up when we are trying to schedule tasks onto servers, where each task has say, a time requirement and, for example, a memory requirement. So two-dimensional geometric bin packing is NP hard, so we look for approximation algorithms. For an algorithm A, the asymptotic approximation ratio is defined as the smallest constant alpha, such that the number of bins used by the algorithm is at most alpha times opt of I plus small o of opt of I. Here opt I is the minimum number of bins needed to pack a set I of items. For example, the next to decreasing height algorithm uses at most 4 times the minimum plus 1 number of bins. So we say that it has an asymptotic approximation ratio of at most 4. The best known asymptotic approximation ratio is around 1.405 due to an algorithm by Bansal and Khan. And on the other hand, it's NP hard to get an asymptotic approximation ratio better than around 1.00026. So the first open problem that we consider is that we want to find algorithms for 2D geometric bin packing that have a lower asymptotic approximation ratio, or we want to get a better hardness result. Let's now digress a bit and talk about the guillotine separable bin packing problem. So here we can see that there's a packing of 8 items into a bin, and by making horizontal and vertical end-to-end cuts, we eventually separate all the items from each other. So packings like this, where we can use horizontal and vertical cuts to separate all the items from each other, we call such packings guillotinable. So this packing that we see here is a guillotinable packing. On the other hand, these packings are not guillotinable because any end to horizontal or vertical cut that we make that goes through the whole bin will cut through an item, and we won't allow that. So in the guillotine bin packing problem, also called the guillotine separable bin packing problem, we're given a set of rectangular items and we need to pack them into the minimum number of guillotinable bins such that each bin is guillotinable. This problem has applications in the metal cutting industry because many machines for cutting metals can only make guillotine cuts. In 2005, Bansal and Lodi gave an algorithm for this problem, which is an AP task. It means that it takes a parameter epsilon as input, and it has an asymptotic approximation ratio of 1 plus epsilon, and it runs in polynomial time when epsilon is a constant. So we've seen two different bin packing problems so far. Now let's see what's the relationship between them. The minimum number of bins that we need to pack a set of items can increase if we insist on guillotinability, but by how much does it increase? This is an important problem in the sheet cutting industry because guillotine cutting machines are often cheaper, but then they also use slightly more raw material. So to precisely define to capture how much the number of bins will increase when we insist on guillotinability, we capture that using a concept called asymptotic price of guillotinability, or APOG for short. This is the minimum value alpha, such that for some constant beta and for each set of I of items, we have opt gi is less than or equal to alpha times opt I plus beta. Here opt I is the minimum number of bins needed to pack the items I, and opt gi is the minimum number of guillotine separable bins needed to pack I. We want to get good lower and upper bounds on the asymptotic price of guillotinability. There is an algorithm for 2D geometric bin packing whose asymptotic approximation ratio is roughly the same as the asymptotic price of guillotinability. So if we can prove that this is at most around 1.405, then we'll get the best known algorithm for 2D geometric bin packing. This is another reason why it's important to get good bounds on the asymptotic price of guillotinability. The best known lower bound so far is 4/3, and the best known upper bound is around 1.691. And it was conjectured by Bansal and Khan that the asymptotic price of guillotinability is equal to 4/3. So this is the second open problem that we consider, that we want to improve the bounds on the asymptotic price of guillotinability. So we've seen two open problems so far, and these are difficult problems, and there hasn't been much progress for the last few years. So we focus on a special case of this problem, that is skewed items. So we say that a rectangle is delta skewed if its width is at most delta or its height is at most delta, where delta is a small constant. In practice, this means that no item is too big compared to a bin. So we address the first open problem for skewed items by giving a polynomial time algorithm for 2D geometric bin packing that takes a constant epsilon as input, and it has an asymptotic approximation ratio of 1 plus epsilon if the items are delta skewed for some constant delta that is less than epsilon. So this is roughly like an AP task for 2D for 2D geometric bin packing when the items are skewed. To address the second open problem for skewed items, we first show that the asymptotic price of guillotinability is lower bounded by 4/3 even when the items are delta skewed. And next we give an algorithm for 2D geometric bin packing whose asymptotic approximation ratio is around 4/3 times 1 plus 8 delta for delta skewed items. And the output of this algorithm is a guillotinable packing. So when delta is very close to 0, we get that the asymptotic price of guillotinability is very close to 4/3. So we get a tight result here. So our results show that non-skewed items are the hard case here. So far we've addressed the two open problems for the skewed case, but for the general case, these problems are still open. So natural next step is to analyze non-skewed items, and then we can try to merge that with the results that we have for skewed items here. Thanks a lot. That's it.
Thank you very much. So again, if there are any questions, you can actually, either step and go to the mic or write them on the chat. I don't see any. Let me ask just a very, very quick question from my side, just to be sure I understand correctly. So the problem for you is not just the delta that is lower than the epsilon. It's not just that it goes into the running time. If that's not a small constant, it's really that that you don't get the approximation bound. Did I get it correct?
I couldn't understand your question.
So okay, my question is the following: if delta is not constant, so then what happens is just a running time problem, or is the approximation that becomes quite bad?
Okay, so in the second algorithm that I talked about, that is that outputs a guillotinable packing, that algorithm does not need delta as input. It's just the approximation guarantee improves if delta is smaller. Okay,
got it. So it's the standard things. So it's like something like 1 plus something order of delta, basically the approximation.
Yeah.
Okay. Good. Okay, if there are no questions, then yeah, we can move. Actually, we're quite on time, so that's good. We can move to the last talk of this first section that will be on again like something related to packing, bin packing, but like a truly asymptotic lower bound for online vector bin packing by Jan Cohen. Good.
Yes, I have some problem screen sharing.
Okay.
Let me see.
Like you see the button or?
Yeah, I need some permission.
Permission. Okay.
Yeah, guys, give me a second. Come on.
Yeah.
Hey, Laura.
Hi, Lisa. Just we have a problem. It seems that the speaker needs permission to share the slides.
Okay, is that like their browser telling them that they need permission?
Yeah.
Okay, so you'll probably have to change the settings for your browser to have the permissions to share your screen.
Is it working now?
Okay, I see it now. Yeah.
Okay, great. Okay, so hello everyone. Today I'm going to speak also about asymptotic lower bounds here for the online vector bin packing. So the problem that we need to pack d-dimensional items. Here are example for three-dimensional items. So we pack the items on top on the others, and we need to pack them into bins when we have max load of 1 in any of the dimensions. So let's see an example for a feasible assignment. As you see, I can in this example, I assigned the item 1 and 4 together. So the total, and we need to verify that the maximum load is at most 1 in any bin in any dimension. Okay, so this is example of a feasible assignment, and the goal is to minimize the number of bins. So this is a generalization for the bin packing problems. Here, instead of 1 dimension, we have each item as the dimension, but not as geometric packing. We just each item is a vectors, and we just sum up the load of each vectors in the bin. So we're going to deal with the online version of the problems, where the input is a sequence of vectors, and the algorithm needs to assign immediately to which open bin is going to assign the vector, or to open a new bin. Let's see a quick example. So the first vector arrive, we must assign it into a new bin. The second vector arrive. Here we also open a new bin and assign the vector to the new bin. The third vector arrive, and we open a new bin. But when the fourth vector arrive, we can assign it feasibly to the first bin without overflowing the bin capacity. So we assign it there. And the fifth bin arrive, the fifth item arrive, and we assign it to the third bin. Okay, and the goal is to minimize the number of bin. So we're going to discuss the competitive, what's the possible competitive guarantees from an online algorithms, and there are two important benchmarks. One is the absolute competitive ratio, where we compare the expected number of bins opened by the algorithm versus the optimal packing. And here's an old result by Gary, Graham, Johnson, and Yao show that the absolute competitive ratio is D plus 0.7, which means it goes linear with the number of dimensions. And in stock 2013, we showed that the absolute competitive ratio for any online algorithm is at most D over log square D. So you cannot get any better than linear in the number of dimensions. Okay, but the motivation for this vector bin packing comes from the world of cloud computing, assigning jobs. And in many cases, we are interested in scenarios when opt is large. And this term of absolute competitive ratio does not capture it. So as I said, bounding the competitiveness of vector bin packing is especially interesting for large value of opt-I. So in the lower bound that I presented earlier, order of log, opt is just order of log D. So think of D as fixed, even 100 or 200. So opt in this case is really small. So therefore, we also analyze the asymptotic competitive ratio, where given fixed D, we want to optimize the optimal number of bins to go to infinity, and then we compare the competitiveness of the algorithm versus the optimal. So the main question of this paper is whether it's possible to get better asymptotic competitive guarantees. Actually, when I thought about the problem, I thought it might be possible. So the only lower bound was for the case of small vectors, and it was just a constant, so it was open. Can we get something between a constant to linear with a number of dimension? And in this work, we show that the asymptotic competitive ratio is also almost linear with a number of dimension, is d over log square d for a sufficiently large and fixed value of d. So actually, these lower boundaries, the constants are not good. So when we for many values of d, we got better asymptotic lower bounds for also medium values of d. We got something like square root of d, but with better constants. So for many values of d, this lower bound is better than the asymptotic one. And we also study the case for small values of these. But in this talk, I'm going to focus just on large values of these on our asymptotic lower bounds. So I won't get into all the details, but I'm just going to let you know what's the original absolute lower bound construction and what are the difficulties to transform it to a asymptotic one. So in the reduction, we did a reduction from vector bin packing to graph coloring. So graph coloring, given a graph, you need to feasibly color the graph in a minimum number of colors such that two adjacent vertices does not have the same color. And there is an obvious reduction from this problem to the vector bin packing. In fact, each vector correspond, each vertex correspond to a vector, and each color correspond to a bin. Okay, the problem in this reduction is that we set the number of dimension as the number of vertices. Okay, so if we try to transform it, to an asymptotic, we don't want this relation from vertices to vectors. So in order to achieve the lower bound for the absolute, we studied an online version of the online graph coloring. I will so this is the online version. When each vertex arrive and reveal its edges to previous vertices, and the algorithm must immediately assign a feasible color. So let me go quickly through this example. So we used a lower bound, but Alderson and Sesgadi, and that showed that the absolute competitive ratio for any online algorithm is n over log square n, and opt in their lower bound is log n, and they prove that any algorithm is n over log n, which yields the lower bound. But as I said, in the absolute competitive ratio reduction, n is also the number of dimension. That means that if I would like to increase opt, that means that I need to increase the number of vertices, which means increasing number of dimension, and I want to get a lower bound for fixed. Okay, so instead, our goal is to increase opt without increasing the number of dimension, but to use same kind of reduction. So instead, what we did, we take the original graph and transform it to a T-click version of it. That means I replace each vertex from the original graph in a T-click. That means a subgraph that any two vertices are connected. And if I have an edge in the original graph, that means any two vertices in these two clicks are connected. So this actually yields a new problem that we call the T-click graph. And this is actually closely related to fractional coloring. If I divide it by T, I get a number between the original coloring number of the graph and the fractional coloring of the graph. And as T goes to infinity, it goes to the fractional number of coloring. Okay, this is an example where the number of coloring is 3, but then the fractional is 2/2, and we'll see that it's closely related to color half of the vertices of each click. But the big advantage, if again the vertex colors correspond to vectors bins, and the big advantage in this reduction, if I have n times t vertices, I only need n-dimensional vectors. Okay, so by letting t go to infinity, I'm making a bigger and bigger instance that's going to infinity without increasing the number of dimensions. Okay, and now the main technical contribution is how to find a lower bound for this T-click. Now, when each time instead of vertex, a T-click arrive, and I need to color every vertex in this T-click. And the main contribution is that we show also for this problem, when we need to color a T-click, is not just one vertex, which give you more powerful in the colors, still the lower bound holds, and still the factor is n over log square n, which yields the lower bound also for the vector bin packing. Thank you. I hope you can hear me.
Yeah, thank you very much for your talk. Okay, so are there any questions on the chat? I don't see any. Okay, we're also a couple of minutes late, so we can maybe end the session here. And let me remind that now there is a discussion phase. The discussion is going to take place in the lobby, so we can all move to the lobby and discover this new room with posters together. Okay, thank you very much. Thanks to all the speakers again.
Thank you.